Here, recording. All right. Well, hey there, everyone. What do we have today? Not that much. I mean, well, we've got a couple problems. So I already posted the video in which I went over the concepts for today's topic, which is surface integrals of scalar functions. This is the natural progression based on the topic that we last covered. At the beginning of chapter 7, we did paths and curves. Now we're doing surfaces. So all the different things you could do on surfaces include parameterize them, find their area. Now we're integrating scalar functions over surfaces. You might even be able to guess what we're going to do in the next lecture, which is integrate vector functions over surfaces. But that's not for today. Today, I just want to do a couple problems related to integrals of scalar functions. And okay, what were those problems? So you already watched the video. You saw I already gave the definition. And I also gave the formula for the average of a function over a surface. So let's apply that to the Sealy noodle, which appeared in a previous lecture, which apparently is also called a helicoid. So this is the same parameterized noodle that we saw previously, right? Where psi of u and v is u cos v, u sine v, and b, for uv in the set -1, 1 cross 0 to 2 pi. But if you say just took this noodle out of a big pot of boiling water, which, by the way, cooking noodles, life hack, use a lot of water and put a little bit of olive oil and a bunch of salt in the water too. It's a pro tip from an authentic Italian. Anyway, so you pull this noodle out of the water. It's a hot noodle. The temperature of the noodle is not uniform, however. The temperature of the noodle is as follows. At a point x, y, z on the noodle, the temperature is given by the square root of x squared plus y squared. In other words, it's the distance from the central axis. And that's the temperature. So the noodle is hottest on its two outer edges, and it's coldest right down the middle. And we want to find we want to find the average temperature, but first, let's integrate the temperature. So that's part A of this problem, and then we'll use that for part B. Okay. So we're going to use our new formula to do part A, which is that the integral of Ps over the surface is the integral of T of the parametrization over the domain of the parametrization times the surface area element u cross T v du dv. Okay, so that's our new formula, and we just have to plug it in and apply it. So let's see. V was -1, 1 cross 0 to 2 pi. T of B will apparently be the square root of u cos v squared and u sine v squared Our surface area element, I think I'm going to use the fact that we've already computed this. So, yeah, we computed this in a previous lecture, 2 lectures ago. Not the last lecture, but the one before. We saw that this is 1 plus u squared. Do I have a v squared? V squared where? In this radical? Oh, this one?
I was just thinking, like, since phi had a z component, like a third component, you wouldn't put that in the radical, in integral?
In this radical?
Yeah.
The reason it doesn't, yeah, why doesn't it appear in this radical? Because this is the temperature, and I gave a temperature which happened to not depend on your z component.
Okay, yeah. For a second, I thought it was like, what was it, the magnitude equation, which is like the square root of the square of each one. Okay, now it's like you're doing the composition of functions. Okay.
Yeah. So I stuck this one in for x, this for y. And then here, I'll just show you really fast. If I went back 2 lectures, and where was that? That was this one. Here's the formula, which I calculated 2 lectures ago. So I'm just going to reuse that formula. Okay. So that's how I get 1 plus u squared. And then let's see, ddu currently. And I can simplify this to be u squared. So let me ask a yes or no question. This equal negative 1 to 1, 0 to pi, u 1 plus u squared dv/du. Yes or no? Oh. So this is a tricky one. I saw a couple no's. I wonder if the no's know why it's no. Anyone who said no want to say why, if they're pretty confident? Has to do with the negative. It does involve the negative. Yeah. Yeah, what's the the square root right here? Square root of u squared. This in general is absolute value, not u, because it's always positive. It's only, you can only disregard the absolute value if u is positive, but u is not just positive. So we cannot disregard the absolute value of u. So I should put absolute value on this. Yeah. Or I could split it up into 2 pieces. Yeah. Okay. Let's see. At this point, there's no v dependence. So I'll just get a factor of 2 pi. Oh, and you know what? I'm going to use symmetry at this point, since this is even. the even function of u. So I'm going to write this as 2 pi times 2 times 0 to 1. And now I can get rid of the absolute value. And so yeah, let me know if you have a question on that. And I can do a substitution at this point. So I'm going to let about w equal 1 plus u squared. So dw du du. And when u is 0, w is 1. And u is equal to 1, w is 2. So then I'm going to get 2 pi 2. And the integral from w equals 1 to 2. And I've got a square root of u and a 1/2. Sorry, square root of w times the 1/2 dw. So 2 pi times the w to the 3/3, 2/3, 1 to 2, which is 2 to the 3/2 minus 1 to the 3/2. Okay, so that was part A. For part B, I'm asked to find the average temperature, which is a bit more physically meaningful, perhaps, than the integral of temperature. I don't know, personally, average temperature is more meaningful than the integral of temperature. It's not so clear to me what the integral of temperature means, but I have a good idea of what average temperature means. On average, like pick a random spot on the noodle. What do you expect the temperature to be at that position? Would be a way to think about it. So average temperature, we'll need the area of the noodle, but I already calculated this in a previous lecture. Let's see. The top. This thing. So the area which we calculated previously, here, let me just show you what we got for it really fast. There is the old temperature. 2 pi times root 2 plus ln of 1 plus root 2. So 2 pi times root 2 plus ln of 1 plus root 2. Cool. Okay, yeah, and so that's the answer. It's not the prettiest looking answer, that's for sure, but that's the answer. Any questions on this problem? Okay. So let's see, what else do I have? Talked about the case that S is a graph. Example of that. So here's an application, by the way. Someone was talking about application. Here's another one anyway. Other than average temperature, is surface mass density, or in fact, surface density of anything. So, for example, if you have mass on a surface, then integrating that gives the total mass. If you have charge on a surface, integrating that gives the total charge. Planet Xanadu has Xanadusians on the surface at a density given by chi. Chi of r is the density of Xanadusians at a position r on the surface. Like if this is planet Xanadu, and maybe you're at some position right there, then chi is the density of Xanadusians. Xanadusians, so they're little aliens there on planet Xanadu. What does the integral of chi represent? Someone want to tell me? Someone who, maybe let me get someone else involved. Someone who hasn't given an answer yet today. What happens if you integrate a population density? A Xanadusian. It's the total population, the mass of all Xanadusians. I like that. It's the total number of Xanadusians, the population. Okay. Xanadusians are like, Martians or Earthlings, but on planet Xanadu. So density is how many Xanadusians there are per unit area. And if you integrate that, you'll get a number of Xanadusians. So the answer here equals the total population of Xanadusians. Just like if you integrate the mass density, you get the total mass. Integrate the surface charge density, you get the total surface charge. Okay. So if there's no questions on that, then that brings me to my main example.
I had a question about the unit discussion. So like you're saying pounds per square inch is not a measure of mass per unit of area because pounds is a force.
Yeah.
But then you were saying tons per acre is, and I was confused because I thought tons was just a lot of pounds.
You're right, actually, sorry. I guess if pounds is not, then neither should tons be. Fair enough. Yeah, you erase both of those. The thing is, people will treat pounds like mass as well, though. So you could be forgiven for treating it as a mass density. Strictly, it's a force. But yeah, good point. Thank you. Okay. So here's a tough problem. Suppose that we have a surface charge density on the unit sphere given by sigma of r equals 1 over the magnitude of the vector r minus p where P is just some fixed vector that lives inside the sphere. R, as usual, or as is often the case anyway, is your position, X, Y, and Z. Oh, Zion, bless your heart, Zion, you're used to the metric system, which we should all be on. I'm ashamed as an American that we're not. But yeah, in America, ton is 2,000 pounds. In most other places, when they say ton, they mean a metric ton, which is 1,000 kilograms, also called a megagram. But an American ton, or maybe it's a British ton, either way, 2,000 pounds is about 900 kilograms, roundabout, something like that. It's not exact, like it's not exactly a metric ton. Yeah, tell me about it, Dimitri. I wish so too. Yeah, and everyone would be happier for that. Okay, so this problem, let's see, we've got a sphere and what the heck? What the heck is going on? That's weird. You seeing what I'm seeing? This circle is bent. Dude, OneNote is glitching on me. That's weird. It's not supposed to do that. That has never happened. Okay, that's better. That's a nice, there's a smoother circle. There's a glitch in the matrix right there. So here's our sphere, actually, is what this is supposed to represent. And I'm going to place it, let's say, with this being the z-axis, and this being the, let's say, the x-axis. And this is a sphere, so it's a 3D shape. You kind of have to imagine. It has depth, and there's also a y-axis, which I'm not going to draw for the moment. I gave a hint for doing this problem, which is to assume that the vector p lies on the z-axis. So if you think about it in terms of symmetry, that's a reasonable assumption. You might as well choose it to lie on the z-axis. There's no direction that is special over any other direction. So it shouldn't matter what direction P points in. Like you could have just, whatever direction P points in, you could define that to be the direction of the z-axis if you want. So we can assume that P is right there, is fixed. And for convenience, how about we let D be the length of P, okay? Now, if you pick some point on this sphere, let's say a point right here. Then this is your position vector, R. By the way, since this is the unit sphere, we know that the radius is 1. And I can create a triangle. It's not a right triangle, though, interestingly. It's a triangle, but not a right one. And this purple vector would be the vector that connects R to P. Yeah. So that's how you go from one vector to another. You do like the head of one minus the head of the other. And check this out. What's this angle right there? In terms of a familiar coordinate system that we all know and love. Anyone recognize what that angle is in there? How about in spherical?
Is
We have
that
a-
phi?
That's feet. Oh, good. Nikhil has the Greek letters down in the Zoom chat. Nice. Okay, yeah. So that's feet. That's exactly our azimuthal angle. I think it's called azimuthal. So let's see. We know that the length of R is 1, or at least for points that are in the sphere. Okay. Or perhaps I should say on the sphere, to be a bit more precise. As in not in the ball, on the sphere, not interior, not in the interior of the ball, but rather on the surface of the sphere. So this triangle that I drew is going to be used as follows. I want the length of the side R minus P. And to find it, I'm going to need the law of cosines. So by the law of cosines, the length of R minus P squared is the length of R squared plus the length of P squared minus twice the length of R times the length of P times the cosine of the angle between them, which is P. And this term is 1, and this term is D. So, i.e., the length of R minus P is 1 plus D minus 2D cos P, all in a square root. Okay, now, oh, D squared, thank you. Yeah. Okay, that's great. It will be helpful if I use some other results, which I don't really want to do now, but it can be proven. So let me give you a fact, which is really useful and you're going to use many times over whenever you integrate on the surface of a sphere. You're probably going to want to use spherical coordinates, and you're probably going to need the following surface area element. So the surface area element ds in spherical coordinates on the surface of a sphere of, let's just say radius capital R for the moment. In the problem, the radius is 1, but I'm going to give you the more general formula, which is that surface area element on the surface of the sphere of radius r, i.e. where rho is r, is r squared sine phi, d theta d phi. Like I said, it's worth memorizing that formula. Guaranteed, because I've taught this class before, and I know some of the familiar questions, I would definitely get questions because students didn't have this formula memorized. So it would behoove you to do it. You're going to use it when you integrate on the surface of a sphere in spherical coordinates, which is exactly what we're going to do in this problem. So in our case, R is capital R is 1. So our surface area element is sine phi, d theta, d phi. This is all using spherical coordinates, by the way. So the integral of our function over the circle is then, let's see, 0 to pi, 0 to 2 pi, over the square root of 1 plus e squared minus 2e cos e times sine phi d theta d phi. There we go. So if you could get to this integral, you're like 90% there on this problem. The rest is just calculus, just like 20B. Right, so just setting this up is the main deal. So let me know if you have questions on how we got to this point. And while you're formulating that, I'll do a substitution to evaluate the integral by, let's say, u. 1 plus e squared d cosine phi. du is d sine phi dt. Yeah, e equals 0. Use 1 plus e squared. I did a little factoring there, and I didn't show my work. Similarly, by the way, at e equals pi. Oh, wait. This is a minus. 0, minus, yeah, I think that should be a minus. Here, I'll just write it out. So it's clear. 1 plus e squared minus 2d. E is equal to pi. Okay, so let's see. There's no theta dependence, so I can just put a 2 pi in front of everything. And after making the substitution, I'll have an integral of 1 over the square root here. And this becomes 1 over 2d du. So I'll get a 1 over 2d du. Minus d squared to 1 plus d squared. Pi 1 over 2d times u to the 1/2 times 2 evaluated 1 minus d squared to 1 plus d squared. Which is pi over d times 1 plus d times 1 minus d. D is less than 1, by the way, since the point P is inside the sphere. If the point was outside, ooh, that's a good exercise, is to see what answer you would get if it was outside instead of inside the sphere. What answer would you get? Yeah, that's a good variation on this question. To do it for the case that the point P lies outside the sphere. Anyway, ones cancel. Get 2 pi times 2d over d, which all is 4. So it's kind of interesting that the answer doesn't depend on the location of the point P. There's an interpretation of this, by the way. This is the electrostatic energy. This is the electrostatic energy at a point inside of a charged sphere. So imagine you could get inside a charged sphere. Is that what Tesla quote? Probably not. But if you could somehow be inside of a giant, like, charged conducting cage, and you yourself were charged, no matter where you were inside it, your energy would be the same. You would be on an energy plane inside the sphere. That probably doesn't make too much sense unless you know a bit about electricity and magnetism, but I'm saying that there is a physical interpretation of this, and it's kind of interesting that you get the same answer no matter where inside the sphere you are. Without going too far afield into the physics, anyone have any questions on the math here? We were able to get the desired answer of 4 pi. Okay, well, you know what? That's all I have for today. Like, there was another problem. I don't think I'm going to do it now. So we can call it quits. And yeah, I'll see everyone on Wednesday, and I'll hang out and answer questions. Dimitri, yeah. So you're right. This actually is very much related to Coulomb's law, and we will see that in about 2 or 3 weeks or so. Yeah, indeed.
For the last question, just to ask about the setup, we just integrate z squared over x, y, and z, or do we want to convert them to spherical here?
So what's cool about this problem and this class in general is there's so many different ways you can do it.
Okay.
So there's multiple ways you could set it up. I can think of the easiest. Generally, the easiest, if you're on a sphere, if you're on a shape that has spherical symmetry, probably you want to use spherical coordinates. So you could set this up using X, Y, and Z, or using rectangular. You could set it up using cylindrical. My recommendation, well, I recommend try all three ways and see which one you find to be easiest. And it's also worth seeing if you could set it up. So like, what would a possible answer be? An integral of what over what? What exactly over what exactly?
If it were like spherical, it'd be from 0 to 1, 0 to 2 pi. The based on the thing, the radius, theta, or phi.
Okay, yeah. So if we are on the unit sphere, by the way, is that a two-dimensional or three-dimensional shape?
3.
Oh, it lives in three space. That much is true. Is it a surface or a ball or a solid?
The sphere is a surface.
Yeah.
Oh, we're computing the average of the surface, not the volume?
Yeah, okay, right. Yes, indeed. So maybe I didn't make it, maybe I haven't talked about this, but a convention is that there's a difference between spheres and balls. So the unit sphere is the set of points where their distance is equal to 1, distance from the origin is equal to 1. Unit ball is the set of points where their distance from the origin is less than or equal to 1. The unit sphere, by the way, here, let's just call this S for the moment, and the ball B. S is the boundary of B. You remember when we discussed boundaries earlier in the class.
Yeah.
The sphere is the boundary of the ball, just like the circle is the boundary of the disk. Sphere is the boundary of the ball. Sometimes write that like this. So yeah, I would challenge you then. Integrating over what set?
Okay, so because this is a unit sphere, we're finding the average of the surface area, essentially.
It's the average, let's see. Well, surface area would be a part of the calculation. So it's this function, z squared. I don't know if a good physical interpretation. It would actually be related to the moment of inertia of this shape. I did a moment of inertia yeah, so that would be the best physical interpretation I could give for why you would do this calculation, is it would be used to calculate the moment of inertia of a hollow ball that is of a sphere. A hollow, if you think of a sphere as a hollow ball, then this would calculate the moment of inertia, and it would give you an idea of how fast it would roll, or how easy it is to make it spin. But you'll need the surface area. and you'll need to calculate this average. How do you calculate the average of F on S? And for starters, you'll need to just find the integral of F over S. So what is that? Like, or I should say, how do you compute that specifically? What exactly are you integrating over what?
My initial guess would be z squared with dx, dy, dz.
Okay. It's over a surface. So if you want to use the surface integral formula, you'll need a parametrization for one thing.
Oh, okay.
So yeah, what parametrization of a surface do you want?
Spherical, and then z squared would be, we could convert z squared into, is it r sine phi?
Let's see. Yeah, so like spherical coordinates are like, let's see, what is it? Rho sine. I think it's rho sine t cos theta, rho sine t sine theta, rho cos phi are usual spherical coordinates. Notice that there's 3 coordinates, rho, theta, and phi. On the sphere, however, you know what one of them is, and the other 2 are your like 2 free parameters.
Okay.
So what can you think of which one of these, if you fix it, gives you a sphere, or which of the 3 coordinates?
Are we not converting? Would it not be radius squared cosine squared phi, because we're trying to find z squared?
Yes, yes. That's true. But if you're on a sphere, then your distance from the origin is, in this case, it's 1.
Right. Yeah.
And there's a bit of redundancy in the notation, because rho is exactly the same as the length of r.
Yeah. In this case, we could drop that out because it's 1, right?
But it's 1. Yeah, right. Good. Yeah. So yeah, I'll just make it 1. So yeah, we don't need it. And we're left with, yeah, that. So those are our coordinates on the surface of the unit sphere. Okay, and then yeah, you said so F, we'll just like you said, it's rho squared cos squared, but rho is 1, so it ends up just being cos squared. Right, it's rho squared, which is equal Okay.
And then you just integrate that over d phi, d theta, and dr, right?
And you can't forget the surface area element. That's why it's usually not as simple as just integrating that, because depending on the parameterization, you'll have a different surface area element ds. Like in general, it's equal to Tu cross dv, du dv. This is the general surface area element. And for this specific case, or for the surface of a sphere case, there's a specific formula for it, which is probably worth calculating at least once in your life. It's a giant pain. You have to do a big determinant and a bunch of derivatives. But once you do that, you should never have to do it again. Yeah, you'll have to do the Jacobian, right? For this here, for this one being like your parameterization, for that being like the of theta and phi. So if the of theta and phi equals that, then there's a specific form of the surface area element. I actually mentioned it today. I didn't really say much about where it came from, which is one of the reasons why I imagine it's going to be hard, right? I mentioned at the time, I said, you should memorize this because it's going to be used, and I always get questions on it. So this is the formula, which I just gave you. It's actually in a homework problem, though, I think. Is it in a problem from 7.3, was it? I think I mentioned, or 7.4. Let's see, I don't actually remember if you do the computation in this problem. So anyway, either way, like you should try the computation at some point, but you should also just know this formula. So this is the surface area element that you'll be free to use.
Okay. All right.
And yeah, Krishna. So Krishna asked if sine phi is the norm of the parameterization. Then yeah, Krishna, yeah, that's correct. It is the norm of the normal vector of the parameterization. Yeah, that's correct. Right. Yeah, it's the length, right, of the normal vector times the theta dphi. You know, it's theta d theta dphi, and so it comes out after much calculation, which, like I said, you should totally do at least once in your life. You find that this equals sine b, d theta dt. More generally, there's an r squared term, except in our case, it's 1, so you don't see the r squared.
Okay, I think I get it. I do have to get going to my next class though.
All right.
But thank you very much.
Yeah, sure. The 7.4, number 11.
Can I ask a question about the previous example?
Mhm.
So can you just clarify how you got the u and the du?
Right here?
Yeah.
Yeah, so my challenge there was to integrate this thing. And you know what? You can ignore the theta part because there is no theta dependence on it. All right. So here, let's just so the challenge then really was just to integrate this.
Okay.
And yeah, so I would ask, what would be a good substitution, or how would you integrate this? And well, you can see that you can do it with a substitution. And like I noticed, hey, if you just make all of this equal to your u, well, then this term here is, it's almost your du. It's your du with just some constant factor of 1 over 2d, as it ends up being the case. Because d is some number which is fixed and constant.
I think I was just confused on where like the d squared went in the u when you took the derivative.
Yeah, because it's a constant, so it's
Okay.
just
I see now. Okay, thank you.
okay, let's see. 7.4 number of surface can be full, but not. Oh, that's a classic. That's the Gabriel's form problem. So let's see, since I assigned this one, I think I can do one that's similar, which I think will suffice.
I just like I was trying to do the surface area and I got to an integral that I didn't know how to integrate. It was like the integral from 0 to infinity, the integral from 0 to infinity, the square root of y squared plus z squared to the 4th plus 1. And then I was stuck. I didn't know if I should use like polar coordinates or something.
Yeah. Yeah, I would let's see. Did I give you a formula for a surface of revolution?
Yeah. Yeah.
Or the surface area of a surface of revolution? Yeah, I did, didn't I?
Mhm.
Yeah, here. So this is
Oh, because this is really the same as like revolving x equals 1 over z around the x-axis.
yeah.
Yeah.
So yeah, this is a surface of revolution. Like I said, this is a famous problem, actually. You can fill this cone. Here, I'll show you. You can fill it with a finite amount of paint, but it takes an infinite amount of paint to paint the surface. You can pour in like a finite amount of paint to fill it up, but if you try and paint the surface, it takes an infinite amount of paint. So that's kind of crazy.
Okay, so I think I can figure out how to find the surface area using the surface revolution. What about the volume though?
What would
Like, do we use like disk method?
yeah, sure. Yeah, you can use disks, I think. It looks like a disk problem to me.
Okay.
What are each of these? What's the area of each of those disks?
The radius is 1 over z. So pi over z squared.
Yes. Well, I guess if we're calling this the x-axis, let's see. So like this, the line where yeah, x is 1, r is 1 over x, or x is 1 over r. Either way.
Wait, r is 1 over x?
Or x is 1 over, well, okay. If you want to view this as a surface of revolution, which I represent, then let's first just make it a one-dimensional problem where we can call this, I don't know, the z or the y, and this the x. In which case, what would this graph be? So
Well, z equals 1 over x. Oh yeah,
Yeah.
because x equals 1 over z is the same thing as z equals 1 over x.
Yes.
So yeah, then the radius of the disk is 1 over x. So the area of one of those disks is pi over x squared.
Yeah. Right.
Okay. Yeah, I think I can probably figure it out from there.
Yeah, and there's modifications of this problem that I've put on midterms before. Oh, check this out. Let me show you a 20B problem that I once put on a midterm. Fall, no, it was earlier than fall. Fall. Oh wait, that was it. Oh crap, go back. Ha, there it is. Or there's one version of it anyway. Oh, this was on a quiz. Yeah, so I gave a variation on that problem. Called it the Horn of Miles, right? Because it's miles long, and there's Miles Davis. Yeah, so see if you could show this. Here's an equation which my 20B students could not justify. They didn't know where this formula came from, but you could now prove this surface area formula. If I have any students that have me for 20B, I mean, there's probably no such students that are here now in office hours, but I think there's some in the class. So they might have seen me give this problem. I should tell them, well, now you can finally explain where the heck that formula came from.
Gotcha. I'll probably just try to do number 11 and call it a day, but I'm feeling ambitious. I'll try that one. Thanks for the help, though.
Mhm. And 0. J hat times sine squared J hat sine squared theta minus, and then minus sine theta cos theta cos squared theta. There we have sine squared theta cos theta sine squared theta sine theta and your sine theta cos theta. In fact, you could even pull a sine phi out. We can pull a negative sine phi out of this. Negative sine phi. In fact, this is negative sine. You recognize what this is? There's a shortcut to this problem if you recognize something at this step. Like you can go ahead and take the length of it. That's fine. Yeah, if you go ahead and just take the length, you could, that's totally fine, but there's a little shortcut if you just recognize what this is of the form. And yeah, you basically said, yeah, I think you, yeah, its length is 1, right? Because this is your position vector. It's your x, y, and z coordinate on the sphere. Yeah, so it's, in fact, we might also call it r hat, since the length is 1. Yeah, so it's a sine phi times r hat. There are, if in general, if this is your position r, then r hat is the vector in the same direction of length 1, and on the sphere, it's just the same as your position. R equals r hat on the sphere. Because the length is already 1. And it's also the normal for the sphere. Yeah, sure, Krishna. Good question. I'm glad you asked. Glad someone's doing the checking the calculation.